Welcome to lesson 3.4. This lesson is called linear programming. The objective is that we're going to find maximum or minimum values in order to solve problems. There's a bunch of definitions here we'll go over in a second, but essentially we're pulling together all the skills from this chapter into one type of long problem. So this is the last lesson of the chapter, and yeah, so like everything is kind of pulled into this one. So what's new about it is that it's a big long word problem, but all the skills necessary are stuff we've already talked about. So first definition, linear programming. It's a technique that identifies the minimum or maximum value of some quantity. That'll make more sense once we're doing it here. The objective function is a model of the quantity that you want to make as large or as small as possible. So that's going to be an equation. Then there's going to be constraints, and those are limits on the variables in the objective function, written as linear inequalities. So those are going to be linear inequalities that we write eventually when we get to the whole problem altogether, that we write and then graph, just like we did last lesson. The feasible region contains all the points that satisfy all the constraints. So when there's multiple inequalities graphed on the same graph, there's going to be a part of the graph that is shaded by all inequalities at the same time. That's going to be the feasible region. All right, and then the vertex principle of linear programming. If there is a minimum or maximum value of the linear objective function, it occurs at one or more vertices of the feasible region. So ultimately, when we have this thing graphed, we're then going to be looking at the corners of the shaded region, and that's going to be where the answer is. So if we have 4 corners, then we're going to have to test all 4 corners and see which one works. Before we do the whole process, we're going to look at a couple parts of the process along the way to build up to it. So the first thing here is actually the third step of the entire process, where we've got inequalities graphed. So these are the constraints. The feasible region, based on, just using the definitions from the last slide, the feasible region is this shaded region. The objective function is given here, and we're trying to maximize it. The vertex principle states that I don't need to test every point in the shaded region, I just need to test the corners. So I'm going to make a little table where I'm testing the each ordered pair. So the first ordered pair is 0, 6. Okay, when I substitute that in to that function, I get 0 plus 6, and I end up with 6. All right, just go clockwise. 5, 6. Now it's just 5 plus 6, and I get 11. The next one is 5, 2. Substitute those values into the function, I get 5 plus 2, which is 7. 4, 0. 4 plus 0 is 4. And then 0, 3. So 0 plus 3 is 3. The one that maximizes is 11. So the ordered pair that maximizes the objective function is 5, 6, and the maximum value is 11. Same thing down here. We're going to test all the same points. So 0, 6, 5, 6, 5, 2, 4, 0, and then 0, 3. When I substitute those values into the function, I get 0 plus 30, right? Because 7 times 0 is 0, 5 times 6 is 30, and I end up with 30. Substitute 5 in for x there, I get 35. Substitute 6 in for x, I get 30. Add them together, you get 65. Substitute 5 in, you get 35. Substitute 2 in, you get 10. Add them together, you get 45. Substitute 4 in, you get 28. Substitute 0 in for y, you get 0. So you end up with 28. And if I substitute 0 in for x, I get 0. 3 in for y, I get 15. So again, this one was minimizing. So the ordered pair that minimizes this objective function is 0, 3. The minimum value is 15. Let's look at the next one. Whoa, one too far. All right, so that was essentially in the whole process, that was the third step. This is the second step where we're actually going to, well, it's going to be the second and the third step. But the first part is we're going to graph the constraints. So the constraints are given to us here. These are these inequalities. So y is less than or equal to 5. That's a horizontal line at 5. So that would be here. It's going to be a solid line. And we're shading underneath it. I'm going to hold off on the shading until the end, though, because it'll be kind of obvious where to shade. I would also be using a straight edge if I was doing this by hand. X less than or equal to 6 is going to be a vertical solid line through 6. X plus y is greater than or equal to 2. I'm going to subtract x from both sides and get y. Woo. Inequality symbol did not flip. Is greater than or equal to negative x plus 2. So I got a y-intercept of 2. Slope of negative 1. So that means I'm just doing this. It is greater than or equal to. So what is this solid line? And we'll be shading above that. X is greater than or equal to 0. Vertical line through 0. Y is greater than or equal to 0 is a horizontal line through 0. So it's above that line, it's below that line. It's to the right of this line, it's to the left of this line, and it's above that line. So everywhere I'm going to shade is in here. All right, so graphing the constraints is done. Find the coordinates of each vertex. Well, the coordinates of each vertex are the corners of that shape. So here, 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 and here. So if I'm going to write out those coordinates, I'll just pick the top left corner. That is at 0, 5. This one's at 6, 5. This one's at 6, 0. This one's at 2, 0. And this one's at 0, 2. Then the last part says evaluate each point into the function. So it's 2x plus 3y. We got p is equal to 2x plus 3y. And we're going to maximize m out. So we'll get both answers. What makes it the biggest, what makes it the smallest? So when I substitute 0 in for 2, I get 0. When I substitute 5 in for y, I get 15. When I substitute 6 in for x, I get 12. When I substitute 5 in for y, I get 15. When I substitute 6 in for x, I get 12. 0 in for y, I get 0. Add that together, you get 12. 2 in for x, you get 4. 0 in for y, you get 0. And then the last one, 0 in for x, you get 0. 2 in for y, you get 6. All right, so the one that maximizes it is the one where I got 27. So that's the one for the max. So the ordered pair 6, 5 maximizes the function, and it has a maximum value of 27. 4 appears to be the smallest number. So the ordered pair 2, 0 minimizes that function for a value of 4. right, so now we're going to do all three steps. So the first step is going to be taking a word problem and writing out, well, defining the variables and writing out the constraints. The second step is then graphing, and then the third step is evaluating the objective function. So the first step is honestly the hardest. That's why we're doing it backwards. It seems weird that we're doing a problem backwards, or at least unveiling the steps for them backwards. But in all honesty, the hardest step I think is the first step. Then I think the second step would be the next hardest, and then the easiest is the third step. So the hardest part is taking the word problem and pulling out all the information you need out of it. So this question says a furniture manufacturer can make from 30 to 60 tables a day and from 40 to 100 chairs a day. It can make at most 120 units in one day. That's all going to be information that we're going to use to write our constraints in a minute. The profit on a table is $150 and the profit on a chair is $65. That information we're going to use for our objective function. How many tables and chairs should they make per day to maximize profit? And then how much is that maximum profit? So answering those questions is going to be the answer to the whole thing at the end. So the first thing is defining the variables. Doesn't matter which one you make which. I'm going to say tables are X just because it came first. So X is going to be number of tables. We're going to let Y equal number of chairs. And P is the thing we're trying to maximize, which is the profit. So let's write out the information. I think I'm going to do the objective function first. The profit is equal to, so we're getting that from this sentence here. I didn't mean to like cross out the sentence, but there you go. That's the sentence we're going to write the objective function from. So the profit on a table is $150. So that means if X is the number of tables they make, 150 times X is the amount of money they make on all the tables. And if Y is the number of chairs they make, and they make $65 on one chair, 65Y is the amount of profit they make on all the chairs. 150X plus 65Y is how much they make a profit on all the furniture, the tables and the chairs together. All right, so that's the objective function. The constraints are based on the limits on what they can make, because obviously if they can make 1 million chairs and tables, then that would be the easiest thing to do, right? But there's constraints on what you can make. Right, there's a limit on the amount of materials you have, a limit on how much time in a day you have, there's a limit on how many employees you have that are making these things. So, right, it's not unlimited. You can't just make 1 million tables and make $1 million of profit. That's not how it works, right? So it says a furniture manufacturer can make 30 to 60 tables. You can write that as one compound inequality. It's probably easier to write it as 30 is the minimum amount you're going to make. So that means X needs to be greater than or equal to X, because X is tables, we define that. And 30 is the minimum, so X is going to be greater than or equal to 30. And then 60 tables. So X is also going to be less than or equal to 60. Again, you could have one compound inequality. All right, the next set of constraints. They make 40 to 100 chairs. Those inequalities are going to look just, it's just that they are going to be based on Y. So then Y needs to be greater than or equal. Y needs to be less than or equal to. Okay. And then we have one constraint left, which is they can make at most units, so tables or chairs. So that means X plus Y, since we're combining both of them in this constraint, needs to be less than or equal to 120. All right, so those are all the constraints. Now we're going to graph that one here. but I'm just going to move that up that way. We created up here, so that'll be easier. Graph over here. All right, so we need to scale the graph because obviously the numbers are bigger than if we just made the blocks 101. So I'm going to, it actually works out nice. There's 12. 12 would be the biggest number we need. If we do it, each block is worth 10. So x is greater than or equal to 30. If we scale it, 0. Each block is 10. So there's 20. 60, 80. The same thing going up. 20, 40, 60, 80, 100. All right. X greater than or equal to 30 is going to be a vertical line through 30. Even though we don't have 30 is between 20 and 40. If I have one, or if I was doing this on paper. A vertical line through 6 part there. Y, those are going to be horizontal lines. I'm going to change the color. Horizontal line through 40. And a line through 100. So basically, is that rectangle. We also have the x is less than or equal to 120. So if I to make this look it might be easier, subtract x, and you're going to get y less than or equal to negative x plus 120. All right, so then horizontal line, I'm sorry, a diagonal line, that 120, and then a slope of negative 1. So essentially, it's going to be a diagonal line. Well, there. I put that in not. Yeah, I think it got messed up down at the bottom here, but I think it's through here at the appropriate place, and it would be then less than that. So underneath that green line, it's going to be shaping everything in this part of the graph. Okay. So again, the question is the amount of things that's going to maximize their profit. So we're going to only focus on the, what color I guess I'll use black. We're going to focus only on the corners of the feasible region. So here, 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 and here. So we're going to test all of those. So the first ordered pair up here in the top left is 30, 90. This ordered pair here is 60, 60. And logic would tell you that since making 60 chairs and 60 tables, you're going to make more money than 60 tables and 40 chairs, right? So I don't really need to test this one because that's definitely going to not be more than this one. The same thing here, making 30 tables and 90 chairs is going to make more money than 30 tables and 40 chairs. So I don't need to test that one. I'm just going to test these two. All right, so we're substituting 30 in for x, so 150 times 30. Plus 65 times 90. So let's figure out what that is on the calculator. I'm not doing that in my head. All right, so when you multiply all that out, you get 10,350. Do the same thing for 60. So 150 times 60 plus 65 times 60. And when I type that in the calculator, you get 12,900. So the answer is this one, right? So the answer to the question is you're going to maximize your profit by making 60 tables and 60 chairs, and the maximum profit is $12,900. I'm going to leave, there's one more on your note sheet. I'm going to leave that for you to try on your own, and that will be the exit ticket. So if you're totally lost and you want to just wait for me to come back on Thursday, first thing in class, and go over that with you, totally fine. If you want to give it a try, see how you do, and then we'll go over it together, that works too. So let me know, how you want to do it. But again, if you want to hold off on trying the exit ticket until I'm back and I'm going to work it out with you, that's totally fine. But yeah, so I'll see you Thursday in class. Definitely come with some questions.